Hello guys, welcome to Self-Help Paths Academy. Let's continue in the orthogonal matrices. So we have some few definitions which we're going to use in order to define them. So let's start with the inner product. If u and v are vectors in Rn in the nth dimensional, then the number u transpose into v, because, I'm saying number, because it is a scalar quantity, is called inner product of the vector u and v. It is usually written as u dot v. It is also a dot product. Okay, how do we define it? If suppose you have u is equal to, say, u1, u2 and so on up to un, and your v is equal to v1, v2 up to vn, since it is in n dimensional, so therefore the inner product u transpose into v, this is like, usually you denote it as u dot v, this is equal to u transpose into v. So this is basically given by u1 v1 plus u2 v2 and so on up to un vn. So this gives us the inner product of the vectors u and v which are in Rn. For example, let us consider the example. Compute u dot v and v dot u when, say, vector u is given by 2, -5, -1 and v is equal to, say, 3, 2, -3. Now let us find out u dot v. U dot v, by the definition, it is u transpose into v. So let us consider the transpose of u, that is 2, -5, -1 into v, that is 3, 2, -3. So this is equal to 2 times of 3 plus -5 times of 2 plus -1 times of -3. This is equal to 6 minus 10 plus 3. So which is -1. So let us find out now v dot u. So which is v transpose into u. So v transpose, this is 3, 2, -3 into u, that is 2, -5, -1. So this will be equal to, by the definition, this is 3 into 2 plus 2 into -5 plus -3 into -1, which is 6 minus 10 plus 3, which is equal to -1. So it is clear from the calculation that v dot u is equal to u dot v, which is equal to what? -1. Okay, so we have one property on the inner products. So in terms of the theorem, say, let u, v and w be vectors in Rn, and let c be a scalar. Then we have u dot v is equal to v dot u. That implies the inner product is commutative. Inner product is commutative. We also saw the example above. Second property is u plus v dot w is equal to u dot w plus v dot w. So this is distributive. It's right distributive. Okay, or addition. Now the third one is c u dot v is equal to c into u dot v, or u into u dot into cv. Okay, so we can write in either of the form. And next property, if suppose the inner product of u and u is greater than or equal to 0, so the inner product of the vector and with itself, if its inner product is greater than or equal to 0, and you have, say, u dot u equal to 0, when it is possible, if and only if your u is equal to 0. So this is possible only when your vector u is equal to a 0 vector. Okay. And also, suppose I take the linear combination, that is C1 U1, C2 U2 and so on up to say CP UP, and I am taking the inner product with W. So this we can write it as, I'll write it down here, C1 into say U1 dot W, C2 into say U2 dot W and so on, CP into UP dot W. Okay. So these are certain properties which the inner product holds. Okay. Now let's see the next one, the next definition, that is the length of the vector. The length of the vector. The length of the vector. So here the length, or also we call it as the norm. The norm or the length or the norm of any vector v is the non-negative scalar. It's a non-negative scalar. Okay. Which is written as norm v. You can read it as norm v. And it is defined by, say norm v will be equal to square root of v dot v, where v dot v is the inner product of the vector. So square root of the inner product of the vector, which is nothing but what? Square root of, if you write it, v1 square plus v2 square, so on up to say vn square. And if I take the square of the norm, that the norm of the square, that is simply v dot v. So this is very important. Okay. So this is how we define the length of the vector. Okay. So like, interpretation, if you see, suppose you have for any scalar c, here also for any scalar c, say for any scalar c, the length CV is modulus of c times the length of the vector. This is the length of the vector v. Okay, it is in short, like if I have norm of CV, this is nothing but what? If I see it's a scalar, I'll take it out, and then it is just modulus of c into norm of v. Okay, so it is this times the length of the vector v. Okay, so if suppose in this case it depends on the length, what we have is, suppose the length of the vector is 1. If the length of the vector is equal to 1, then we call that as unit vector. We call it as a unit vector. Okay. And then if we divide the non-zero vector by its length, that is multiplied by say 1 upon norm v, then we are obtained a unit vector u, because the length of u is 1 upon norm v into the norm v. Okay, so basically we are actually obtaining the unit vector by dividing the non-zero vector by its length, and it's actually then that is multiplied by say 1 upon norm of v, we will get the unit vector. So this process of creating u from v is sometimes called normalizing v. Okay, so and we also say that u is in the same direction as v. So what we are trying to obtain is, we are trying to obtain we are by normalizing that given vector, non-zero eigenvector, by dividing it with its unit vector. Okay, so we'll be getting the normalization of a given vector. So I think we will see that in the with the help of examples. Okay, so for example, let me see the example where you have say v equal to 1, -2, 2, 0, and we have to find say the unit vector, find the unit vector u in the same direction in the same direction as v. Okay, same direction as v. So let us see how do we do it. So first what we do, we have to compute the length of v for this. So given this v equal to, let us see, this is 1, -2, 2, 0. This is given. So first we compute the length. The length is what? Norm v. So either you can find out norm v, or you also know that norm v square is v dot v. We'll find out that. So here now v dot v is simply what? It is it's transpose into, this is by the definition, it is v transpose into v, or it is simply square root of v1 square plus v2 square. It's a same term, because we have four here, four entity, 1 square plus -2 square plus 2 square plus 0. I'm not taking square root because I'm taking a norm of a v square. Okay, so simple, it is 1 plus 4 plus 4, which is equal to 9. Okay, so here what we have, norm v square is equal to 9. This implies your norm of v is 3. So I'm not taking the, since it is plus or minus 3, but the length should be positive, therefore we are taking only the positive entity, that is 3. Okay, then we have already discussed that how do we get the unit eigenvector by dividing it with its norm, right? So then multiply v by the vector v by 1 upon norm of v. So dividing by its norm, okay, to obtain u. So u is basically what? It is v divided by its norm. So we have already our norm, that is 3, and v also we have. So it is basically 1 over 3 times of v. So 1 over 3 times of v is what? It is 1, -2, 2, 0. So the resultant vector, that is 1 by 3, -2 by 3, 2 by 3, 0. So this is your unit eigenvector, sorry, the unit vector, or we have, in other words, you can say that you normalize the vector v into this. So just to have a real check, if you see, just take the norm of this, that is the length. If you observe, it is simply 1 by 9, 4 by 9 plus 4 by 9, which is 9 by 9. So square root of 9 by 9, which is equal to 1. So if you see, the length of this is equal to 1. So it is the unit vector in the direction of v. So that's how we will actually find out the unit vectors in the same direction as the given non-zero vector. Okay, so that's the method. And then let us see now the next one, next definition. What we want is distance in Rn. Okay, so here for the definition says, for u and the vector u and v in Rn, the distance between u and v, which is written as distance between u and v, which is nothing but the length of the vector. Okay, it's the length of the vector is the length of the vector u minus v. That is, distance between u and v is simply the norm of the vector u minus v. Okay, so this is the distance of the vector u and v in Rn. So let us see one example. Say compute the distance between the vectors. Say you have u equal to 7, 1 and v equal to 3, 2. Okay, so here u minus v is equal to, first let us find out u minus v to find out the length. U minus v will be equal to, it is 7 minus 3, 1 minus 2, which is equal to 4, -1. Okay, so therefore what is the distance? It is norm of u minus v. So it is here, this is your u minus v. So norm of u minus v will be square root of 4 square plus -1 square, which is simply 16 plus 1, which is root 17. So that will be your norm. Okay, that is the distance between the vector u and v, how you find. Okay, then if suppose you have got the three vectors, all right, suppose u is u1 u2 v3 and v is equal to v1 v2 v3, then just I mean, like, in case if you have u is u1 u2 u3 and v is v1 v2 v3, then distance between u and v is still norm of u minus v, which we find by using square root of u1 minus v1 the whole square, u2 minus v2 the whole square, plus u3 minus v3 the whole square. Okay, like this. If it is up to n, you can just do it up to the n terms. All right. So this is how you will be finding out the distance between the two vectors. All right. So now let me quickly define the orthogonal vector by all, because I'm going to use the inner product definition for defining it. So that's why we gave all these definitions. Now we define the orthogonal vectors. Okay, let us define the orthogonal vectors. The two vectors, or we can say the two vectors u and v in Rn are orthogonal to each other when if their inner product u dot v is equal to 0. If their u dot v is equal to 0, then we say that those two vectors are orthogonal. Okay, and a very interesting part is, if you take a 0 vector, okay, if you take one of the 0 vector with any vector, okay, any non-zero vector, then 0 vector is orthogonal to every vector in Rn. Why? Because you take 0 transpose with any vector v, you will get 0. This is true for every v. So hence 0 vector is orthogonal to each and every vector. Okay, so this is very, very important with respect to orthogonal. So orthogonal in terms of the inner product, when you see, it is if the inner product of those two vectors are 0, then we say them as orthogonal vectors. Okay, it's very important to understand the orthogonality in terms of the inner product. Okay, so then we have for example, now let us see the how do we actually compute. If we have, suppose, compute the quantities using the vector. Suppose you have got u is equal to -1 2, v is equal to say 4 6, and you have to find out whether u dot u and v dot v and u dot v. Okay, find out v dot u. So just find these answers, because these are inner products. I think you can find them out. All right, so just find out all these vectors, and similarly you can take also comment your answers in the comment box, that what you're getting. 3 minus 1 5, and say you have x equal to 6 and -2 3. These are all simple examples. I want you all to practice them. So just find out w dot x and x dot x. Say w dot w. You can also find out the w dot x upon x dot x. Okay, into x, you just check. So these are the practices which you can do. Just find out the inner products and multiply with the given vector. Just check randomly what you will be getting. Okay, I think these are the I mean, like, questions which I'm giving you to practice some of the inner products. And I think you can also find out the norm of w, find out a norm of x, and also you can find out the distance between w and x. You can find out. Yeah, so these are some of the I mean, like, entities which I'm giving you to practice them. And also, yeah, and also I think, let me give you one more example where you'll be finding the unit vector. Find the unit vector in the direction of the given vector. Say I'll give you the vector as, say, u equal to -30 40. So find out the unit vector in this direction. So this is 1. Let me give you another vector. So minus 6, 4, negative 3. So what you'll be doing, guys, in when you want to find out the unit vector in this direction, you'll be finding out the whenever you want to find out the unit eigenvector, first find out the norm of the given vector. Okay, compute the norm. All right. Like if you want to find out the this unit eigenvector, so you'll be finding out the norm of u. If you want, you can just take norm of u square and then take a square root, up to you. Just find out norm of u, and then you'll be finding out the unit eigenvector. Maybe say v, you want to find out v will be what, u divided by the norm of u. Divide the given vector by its norm, you'll be getting the unit vector in that direction. Similarly for this also, if you take this as some w equal to, then first find out norm of w, and then you'll be finding out, for example, the unit eigenvector, you are denoting it by w dash. It is simply w upon norm w. That will be your unit eigenvector in the direction of w. Okay, so do all these examples and comment your answers in the box. I think maybe in the next video we'll continue the next discussion. Okay, so we will be discussing about the orthogonal sets and some of the properties, how they are related to linear dependency, all those discussion we will do in the next video. Till then, take care, guys. Bye bye.